of conservation momentum, which is the best application is collisions. So 3 types of collisions, and I'll tell you what they all are. The first one is what we call an inelastic collision. And so the key criteria for an inelastic collision is that you have 2 objects. Again, it could be 3, but usually you just deal with 2, okay? 2 objects, they don't stick together, and some kind of kinetic energy is lost in the collision, and that would be during like a little bit of friction between the objects as they collide, or as a bit of sound, and you hear a click when the 2 things collide. I'm thinking crocono chips when I think of this. Another one would be you drop a tennis ball onto the ground. The tennis ball, you hear the bounce, right? And you know the ball doesn't come up to where you dropped it, okay? That's a key, that's inelastic. Some of the energy is lost, okay? Because otherwise you'd catch the ball exactly where you dropped it. If you've got a super bouncy ball, you can sometimes assume them to be elastic collisions. But if it doesn't, you drop your tennis ball and to catch it again, you have to lower your hand. That means it's inelastic. So what does that mean? Well, first of all, the thing is that most collisions are. So if in doubt, you treat a problem as an inelastic collision, okay? If there's not enough any other information. And it means you can apply the formula of conservation momentum, which we learned in the last lesson, okay? And that's the only formula you can use right here, okay? So in the case of 2 interacting or colliding bodies, and again, we just really deal with 2, this is the formula used. We learned this formula last time, okay? So that is a type 1 inelastic collision. Pause if you need to, but I'm moving on. Okay, type 2. A totally inelastic. So last was just elastic. A totally inelastic, what that means is you have 2 or more, but usually 2 objects at the beginning, and they stick together. Okay? The example, and I'm sure I do an example of this, like someone gets rear-ended and the 2 cars are stuck together after, or Mr. Resto had a wicked accident. It wasn't him driving, it was actually his ex-wife, but she was pregnant too at the time, and they're driving on the 401 right near the airport, and a transport truck comes behind them and bumps into them, and it kind of cuts into their lane and bumps into them. They're stuck. They're stuck on this transport truck, right? That's a collision where they're stuck together. So anytime 2 things stick together, you have an totally inelastic. So totally means that the 2 objects stick together. So what formula applies? Well, conservation momentum always applies. So yes, it applies. And the equation that you end up with looks like this. Here's your 2 bodies at the beginning with their own momentums. At the end, they have a common velocity, right? Because they're stuck together. So it has their total mass, the sum of their masses multiplied by their new common velocity, which is the momentum of the system afterwards. So it's still momentum before equals momentum after. That's still true. It's just that they have a common velocity afterwards, so there's only sort of one velocity you have to worry about in the end. Okay, the third type of collision is the most difficult one, and it's also the least common, though sometimes you can assume elastic. So an elastic or a totally elastic, however, we read. Long story short, by the way, in the question it'll tell you it's elastic. That's the key thing. But the ways that you could identify is, first, the objects can't stick together. That's a criteria. And there's no kinetic energy. So again, this would be like you have a great super ball and you drop it and it does come back to the height. Right? It's such a nice springy ball. There's a little friction in the interaction with the ground and it comes back up. Here's my examples. Another one would be, and of course we don't regularly, on purpose, pound protons together, but at the Large Hadron Collider, something like that, they might. And what happens when you try to collide, if it's 2 protons, normally the repulsion between them, they won't actually touch. So they'll get really close to each other and then they'll repel each other, and they never actually lose any energy because they never actually touch, right? So there's no friction or anything like that. Again, it doesn't happen. I have a nice little example though, if you want to, and it's not a lab, but I'll get out the collision cart, my air track, and if you put 2 magnets, opposing magnets, as long as you don't ram them together too fast, if you have, say, 2 south poles pushing towards each other, they'll turn around, right, and just start going in the other direction. They don't actually touch. So you could call that a collision. It's an interaction between them, but they don't actually touch. So therefore, you haven't lost any energy. So you have two formulas you can deal with conservation, with an elastic collision, totally elastic collision. The first one is conservation of momentum. Okay, right here. The second one is conservation of energy, and I'm dealing only with kinetic energies. And the reason only kinetic is, you're assuming there's no height differences or anything like that going on. It's just two objects running into each other. The total energy of the system before equals the total energy of the system after. And just, if you look what I've done here, is I've just canceled out the halves. Okay, so here's the first formula. Here's the second formula. And it's not that elastic energy is more difficult, but I can make the questions harder. Or your textbook can make your questions harder. Your first year prof can make your questions harder because you now have two equations. And two equations can mean you have two unknowns, right? Just by virtue of the system, if it's just a regular inelastic equation, I can't give you that many unknowns, otherwise you won't be able to solve it. But I can add the complexity of the problem in inelastic. Okay? So the summary then, when you're dealing with a collision problem, which we'll do in the next video, is you'll determine what type of collision using the information in the problem, and then you'll choose the appropriate formula. And here's the formulas. If it's inelastic, this is the only formula you can use. So obviously when I give you the question, I'll give you enough information that you can figure out everything but one of these as a given, and then you'll rearrange the equation and solve for the last one, right? On an inelastic, this is the equation, and same thing, only one equation. So trust me, I'll give you in the question enough to solve for everything, like to give you everything but one, and then you'll put it in the formula and sub and solve for the one thing you don't have, right? Elastic is harder because what I will do, first of all, I'll tell you it's elastic. Okay, you'll have that information, so you'll know, the part you'll have to know is these are my two formulas, and probably I'll give you the two initial speeds in the masses and ask you to find the two final speeds. That's usually what happens. So because you have two equations, I'll ask you to find two things. And it's harder. Like, just trust me, when you do the example, you'll see it's really ugly because you're dealing with squares here. And you're applying substitution rules with something that's squared, and it's painful. I don't put it on tests. On a test, you need to know what elastic is, be able to identify that something's elastic. I don't actually ask you to do this whole rigmarole on a test just because it takes too long. Okay? But you do on your assignment for sure. Okay, I'm going to stop this video now, and I'll start the examples as a separate video.